Okay, so I've been asked to prepare like an introductory video to Bayes' theorem, and I thought, yeah, that's a good idea actually. I think because sometimes there is a bit of a kind of barrier to adoption with Bayesian methods, especially if you're a bit unlucky and if you read something that's a bit philosophical. So if you start reading about Bayes' theorem for the first time and suddenly you're faced with things like aleatoric and epistemic uncertainty, I think it can make it a bit difficult to understand, and really, in my opinion, you can kind of just see it as a tool, and there's times when you can use it, and there's times when you can't, and it's just the philosophical stuff is interesting, but you don't necessarily need to know that to be able to make good use of Bayesian methods. So Bayes' theorem really, it's just one equation, so it's just probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. And when might we use it? Well, we have a problem where we're interested in working out the probability of A given B, and we'll show an example in a second. And let's say that this is actually quite difficult to do, quite difficult to kind of process directly. Well, when we write down Bayes' theorem, it lets us write down the inverse problem, probability of B given A. So really, so I'm being quite kind of general here, but it lets us write down this other, like I say, this inverse problem. So if we can say something a bit more sensible about the inverse problem compared to this, we can have a better go at this thing than this thing, then perhaps, Bayes' theorem is going to be a useful tool for us. So as an example, let's say we've done some tests in the lab, and as a result of some input X, we've witnessed these observations Y, and they happen to look a bit like this. Okay? What we think is that there's a kind of linear relation between X and Y. But there's also noise in our observations. So these data points have been corrupted by some kind of measurement noise because of the sensor we're using, for example. Okay, so first of all, we think there's this linear relationship between X and Y. So it's something like this. So we've actually proposed a model. So our model is that this line, so the equation for this line is given by, so f is a function of x. I'm going to say it's also a function of a parameter theta, where theta just controls the gradient of the line. And ultimately what we're going to try and do is estimate theta from our data. Now I said earlier that we think actually we have a noisy sensor, and let's say that we actually have a pretty good idea of how noisy that sensor is. So let's say that we did some separate tests and we realised that the sensor actually has kind of Gaussian noise. And that lets us specify a noise model. So what I'm going to say is that Y, which is, remember, that's one of our measurements, that's what we've observed through our sensor. So let's say the ith measurement of Y is equal to, we believe there's this linear relationship, so f applied at input xi with gradient theta. But we're going to acknowledge that this sensor is noisy, so there's also added, this noise term was added to our observation. And the noise term that has come from a Gaussian, and it's got variance sigma squared. And for now, to keep things simple, let's say we did some other tests in the lab, and so we think we have a pretty good idea of what sigma squared actually is. And then the situation we've got is we want to realise an estimate for theta, the gradient of the line. So we write down, okay, well, let's write down the probability of theta given all of our data Y. So because we have uncertainty in our observations because of this measurement noise, there's uncertainty in what theta could be as well, and we want to capture that. So we want to find a probability distribution for this gradient, given that we've seen these observations. So I should say that the capital Y there represents basically just a set of all our observations. So let's say Y1 to Y capital N. And so we look at this and we think, well, this actually might be, this is quite difficult to do. Let's say we can't do any more tests in the lab. How exactly are we going to write down this probability distribution? It's not immediately obvious. Well, okay, let's write down Bayes' theorem, and then we'll look at the inverse problem. So that's now the probability of y given theta times the probability of theta divided by the probability of y. Okay. So the first thing we're going to do to make our lives a bit easier is we notice that this thing on the denominator is a constant, as in it's not a function of theta at all. So we can actually just say that probability of y given theta is proportional to these two things. So now this is where we can think about our inverse problem. So this is saying, well, what's the probability of y given theta? So is there anything sensible we can say about that? This thing, I'll use a different colour. So this thing is called the likelihood. And there's a reason for that, but we won't go into it here for now. We can go into that in later videos. But it's this inverse problem. So it's saying, well, if you really believed in this particular value of theta, then what's the probability that you would have witnessed those observations? And we can find an expression for this because we already have this noise model. So what that noise model is telling us is that the probability that we would have realised observation yi if we really believed in theta is equal to normal distribution with the argument yi. Then the mean is the prediction made by our model. So again, we pretend that we really believe in this model. And it's being corrupted with noise and variance sigma squared. And then if we also, what we've assumed here is that the noise is independent for different observations. So a particular value of epsilon for y1 will have no influence on what epsilon will be for y2 and so on. So that means that the probability of seeing that entire set of measurements given theta is now just the product of all of these distributions over yi. So we can just directly go ahead and write that here. So now we have an expression for the likelihood. So here we have this situation where, because of this noise model that we've decided we feel comfortable with, we can actually say something about this inverse problem, probability of y given theta, even though it was quite difficult to say something directly about probability of theta given y. Okay, so now we've got one more term to deal with. So this thing, which we will make green, so this is called the prior. What it is really is it's a probability distribution over theta, but it's not conditional on y at any point. So you're not allowed to write this as a function of y. This is usually interpreted as a probability distribution that represents your, let's say, your kind of knowledge about theta, this gradient term, before you did the experiment. So that's the way it's usually interpreted, but mathematically, what you can say is that it's not allowed to be a function of y. So we might, in this case, say we think that, so I'll just go over here. Let's say that before we did the experiment, we weren't really too sure about what theta could be. It could be positive or negative, for example, and so let's say we just put a Gaussian distribution over that as well. Let's say we gave it it was zero mean and unit variance. But this is entirely up to you. It's kind of user subjective, which makes some people feel uncomfortable. But basically, it's saying that this posterior distribution is a combination of what the particular user thought before the data arrived, and through the likelihood, information that's contained in that data. So there is a kind of, a nice logic to it. And if you view Bayes' theorem just as a tool, basically, if you think for your particular problem you don't feel confident specifying this thing or this thing, then it's not the right tool, basically. And that's that. Okay, so now what we can do is we've got a full expression for probability of theta given y. We know it's going to be proportional to the likelihood multiplied by the prior. And at this point, you've kind of got everything you need. So at the most basic level, what you can do now is you can plot, let's say, theta on the x-axis and the probability of theta given y on the vertical axis, and we can try different values of theta, and we can just plug them into this equation, because now we have this whole expression will let us evaluate the probability of theta given y at any of these points. So now we can just try different values of theta, plug them into this, and we'll realise, hopefully some points, and we can join them up, and there we have it. We have something that is at least proportional to the probability distribution over theta given y. And the fact that we're only proportional to doesn't matter, because obviously you can see that this value of theta is still the most probable. Whether or not you multiply this thing by a constant, it doesn't matter, that's still true. So it turns out there's more stuff we can do actually in this particular case. We can in fact rearrange this completely to get to show that this distribution over y is actually a Gaussian distribution. We can also treat sigma squared, the noise variance, as being unknown, and we can realise probabilistic estimates for that as well. When these expressions, especially for the likelihood, are intractable, there's still other tricks we can play. There's kind of sampling tricks we can play to try and get samples from this this distribution here, probability of theta given y. But that's basically it for an introduction. Bayes' theorem is a tool. If you have a situation where the inverse problem looks better than the original problem, and you can say something about this, and you feel comfortable saying defining a prior as well, then Bayes' theorem is a tool that you can use. If you can't define this, or you can't define this, then Bayes' theorem might not be the tool for that particular problem. So I think in the next video we will look at how we can actually rearrange this to get a closed form solution for probability of theta given y.